Hey everyone. Now I'd like to talk a little bit about vectors. And I implied we were going to talk about vectors after our last video on measurements. And really our discussion of vectors is very similar to our discussion of measurements, because a vector has measurement properties to it. So in this little bit of a section, I'd like to talk a little bit about what it means to have a vector, what are properties of a vector. I'd like to talk a little bit about how we express these vectors, how they can look different in different kinds of coordinate systems, what a coordinate system is, as well as how to add and multiply, subtract these vectors with respect to each other. So while there are a lot of examples that are in the Canvas shell, and I encourage you to look at them, I'm going to focus primarily on a couple of Mathematica simulations that illustrate some particular properties, as well as one example that's not in the notes, but it's akin and related to some things that are already in those previous presentations. So as we get started, I'd like to go to the OneNote pages, very much like you see as you go through the Canvas notes, so that we can talk a little bit about what vectors are. And really what we were talking about before with measurements, when we said that there was some unit dimensionality as well as some number of those units that we have, vectors have one additional thing. They also have a direction. And when we want to distinguish between these two types of properties, we say that the one that does not have direction is something called a scalar, and the thing that does have direction is called a vector. There can still be a number. There is still a magnitude. It's just the vector has one additional thing. And what are the differences between these types of properties? Because we certainly have scalars that we're going to deal with. Time is a perfectly good scalar. Mass is a perfectly good scalar. I mean, we would never say 15 seconds to the right. I don't know what that means. Or 20 kilograms up. These are just quantities that really, by default, do not have any direction. And others that we'll see are speed, distance, energy. But then there's also properties where we have to keep in mind what direction we're going. So for example, if I was to ask you to go 50 miles away, it turns out that which direction you go is important. If you were to go north 50 miles, you end up in, say, Jupiter. If you were to go west 40 miles from Boca, you end up in the Everglades somewhere. And if you go south 60 miles or so, you end up down in Miami. So you have to say not only how far to go, but what direction to go. And if you don't know anything about the direction, you could end up at places that don't necessarily mean a lot of sense to you. Similarly, pushing something to the right and pushing something to the left are different ways to push an object. It's not going to do the same thing. Whether we are moving to the right or we are moving to the left, those look different, those act different, and those are going to put us in different places. So these are what different kinds of quantities, scalars and vectors are. Now the way we typically express a vector quantity is in two particular ways. One of them is a Cartesian sense. We say, hey, how far to the right or left a vector is and how far up and down a vector is. On a map, this is akin to saying go 3 blocks east, go 5 blocks north. This is a Cartesian way of putting together a net displacement. You start at some location, your home, you end at some location, your friend's home. But another way to talk about that is if you had a helicopter, and maybe if you're taking this class in Boca, it's very possible that you do have a helicopter. But let's just say rather instead that it's as the bird flies. Then you don't have to worry about staying on roads. You can just go in a straight line. And then all you need to know is a magnitude and what direction to go. On city streets, you have to follow the grid. But if you don't have to follow the grid, you're a bird, then all of a sudden you can work with magnitude and direction. But either of these ways of getting from your house to your friend's house will have you starting and ending at those positions. So we see a little bit of the trigonometry here associated with trying to describe a vector r with these two different kinds of techniques. So maybe we start at our house, we end at our friend's house, we happen to be going to the right some distance, we happen to be going up some distance, or going east some distance, going north some distance. Fine, whatever. We could have gone in a straight line if we had picked just the right angle. So how do these different quantities relate to one another? Well, how much xness we have, how far the vector goes in this x direction, we need to know what the hypotenuse of some angle is, and we need to know a right triangle. The way we've set up the coordinate system is that the x direction and the y direction are perpendicular to each other. Because they're perpendicular to each other, that means that this angle in this corner here is a right triangle. And because this is an x projection off of the y-axis, this is a right triangle, 90 degrees. And down here in this corner, this is a right triangle, 90 degrees. And because of that, up in this corner, we've got a 90-degree angle as well. This shape is a rectangle. So it has 4 right angles in it and associated with it. This x length is the same as this x length. This y length is the same as this y length. It really is a rectangle. So that means that the angle r is a hypotenuse. Okay, we've got a right triangle here, we've got a right triangle here. And so if I want to describe how far the vector goes, right or left, x or y, x or negative x, east or west, I need to know what this angle is, and I need to know the hypotenuse. And so knowing trigonometry, this x component is going to be the hypotenuse times the cosine of this angle, r cosine of theta. The y component over here, this is the opposite side. So sine theta is going to be this y component over r, or rearranging terms, y is going to be r sine of theta. If we were to write this thing in terms of theta, this is exactly what's going on. But sometimes, in some problems, we're not given theta. We're given phi. And we can still write all of that same stuff if we wanted to. So now, instead of having an x component being r cosine of theta, we could just as easily say that writing in terms of phi, where this is the opposite term, we could write the same thing as r sine of phi. This adjacent side, now associated with y, is now going to be r cosine of phi. So depending upon which of these angles we have, these expressions could look different, but numerically they have to be the same. This vector has some length and it has some angle. That's how we talk about it in a polar sense. But it also has extent in the x direction, extent in the y direction. That's how we talk about it in a Cartesian sense. And that's how we relate the two. Just as a quick reminder, oftentimes, if we're talking about components, what we're trying to do is project a vector onto two different axes that are perpendicular to each other. Well, what's the advantage to that? So here we have this one vector. It's pointing from our house to our friend's house, fine. It's nice, one single vector, but it's in some weird direction. And so if I wanted to figure out how long this was by mapping it onto a grid where maybe I went 4 blocks east and 5 blocks north, it's not intuitively obvious off the top of my head how long this vector r is. I could find how long this vector r is using the Pythagorean theorem, great. But sometimes, depending upon the problem, it might be more advantageous and easier to do math if instead of working with one vector in a weird direction, we work with two vectors that are in easy to work with directions. One of these vectors is only in the x, one of these vectors is only in the y, and you see that if I do the x vector and then I do the y vector, that gets me to the exact same position as just going along the straight line. These vectors have different lengths associated with the trigonometry, sure. But some problems, I don't care about the full vector. I only want to know what the components are, and it could be easier to do. So that's what we're talking about here. We have some vector. It can either be pointing in a weird direction and have some length, or we could be working with two components of the vector added together that make this resultant vector. Now, that being said, we've talked a little bit about magnitude, we've talked a little bit about direction, we've talked a little bit about coordinates and components. So one thing that we need to remember, the one big addition that we have from going from scalar quantities like mass and time, where there's a magnitude and sure there's a unit, as we move to vectors, we're adding this one thing, direction. And we don't want the direction to mess up the unit, and we don't want the direction to mess up the number. We don't want it to change its length. We don't want it to change its dimensionality. We just want to say what direction it's going. And to do that, we come up with something called a unit vector. And so if we've got some vector quantity, here in this case it's position vector, that position vector has some magnitude. In this case, that's a number and a unit. So 5 miles, 6 miles. But then we have some unit direction. The unit direction is usually signified by this hat. This hat tells me that this vector has a length of 1. Not 1 unit. There's no meters. There's no meters per second. There's no newtons. There's no units with this. This only has direction. That's it. And the length of this unit is 1. Okay. So then that tells me that maybe I wanted to move some displacement. 5 miles in the x direction, 6 miles in the y direction. This is indicative of a plot that looks like this. I want to go some distance in the x, some distance in the y. And if I do both of those things, it's the same thing as having just done the one thing in the first place. The start and end points remain unchanged. And it really doesn't have to be for particular problems just exactly like this one. So we could go to Mathematica, for example. And maybe I wanted to look at how components of a vector compare with a magnitude and direction. And so here I've got some vector. I can make it any length. I can have it point in any direction. And you see here that all of my directions are measured with respect to the positive x-axis going counterclockwise. There are advantages to that, and we're going to see in a little bit why that kind of measurement is calculationally convenient. It doesn't have to be that way, but let's just say it is for right now. Here this is an angle 0, angle 90, angle 180 degrees, 270 degrees, all the way around to 360 and wraps around again. Okay, we can have it be any length that we want. And so let's say we're dealing with polar coordinates. And I wanted to look at some vector that was maybe 2 units long, pointing at 30 degrees. So each of these angular measurements is 15 degrees. Each of these circles adds another meter. So 2 meters at 30 degrees is a vector that looks like this. But we see that this is not the only way to talk about this vector. This vector could be talked about in a Cartesian sense. It looks like this vector has some x-ness to it. It goes to the right some distance. It goes up some distance. And so those could be described, the x-ness, by looking at the cosine of 30 degrees times this hypotenuse. The y-ness, the sine of 30 degrees times the hypotenuse. And so we see that x and y are both positive because this is a vector that goes to the right and it goes up. It goes more to the right than it goes up, and you see that because x is bigger than y. So what if we were to have this vector now pointing, let's see here, this is 40 5 degrees short of 180, so this is 135, but it's still at the same length. It's still too long. Now, if we were to look at this in a Cartesian sense, and we can give a little bit more fine detail, this is a vector that's going left and going up. It's not going right and going up anymore. It's going left and going up. And that's why it has a negative x component. It has a positive y component because it's up. It has a negative x component because it's left. Because this is a 45-degree angle with respect to the y-axis, a 45-degree angle with respect to the negative x-axis, this is a 45-degree angle trigonometry. X and y are the same in magnitude. They have different signs because of the leftness and rightness, upness and downness. But this is how we can talk about those different vectors and how components and magnitudes and directions all relate to each other. Okay. Now that being said, we want to look a little bit at things that we can do with vectors. What are some properties of vectors? What are things that vectors do and what do they not do? And primarily what I want to look with here is what does it mean to have a vector? What is two equivalent vectors going to be? Eventually we're going to be creating equations, which means that there's a vector on the right side of the equal sign and there's a vector on the left side of the equal sign. Those two vectors have to be the same. So what does it mean to have two vectors that are the same? How could I change and alter vectors without changing any of the physics of the problem? Later, we're going to want to add vectors together. So what does it mean to add vectors? What does it mean to subtract vectors? What does it mean to multiply vectors? And so that's what we're going to do for the remainder of our time in this video. And the first thing I want to look at is what it means to have vector equality. So here we have two vectors. It's pretty easy to see from this picture that they have the same length. It's pretty easy to see that they're pointing in the same direction. But we see that they're not sitting at the same position. And that's okay. Because a vector has a length, which is a number and a unit, and it has a direction. Vectors do not have positions. Vectors don't have positions. And because vectors don't have positions, these two vectors, even though they're not sitting at the same place, are the same vectors. They are equal to each other. Going 5 miles to the east and 10 miles north from campus is the same thing as going 5 miles east and 10 miles north from the Jupiter Lighthouse. Is the same thing as going 5 miles east and 10 miles north from, I don't know, Lauderdale by the Sea, or whatever you want to have. You're going to end up in different locations, but the way you move, the direction you move, how far away you are from where you started, those are what a vector describes. Those are the same. So these are equal vectors. Now that being said, now that we know about vector equality and that I can move vectors around, how would we add vectors together? And really what we're doing is very much what we're doing as we move around on a map. We might go in some particular direction for some distance, and then we go and do something else, and then we go and do something else. What you are doing by adding that word then is adding on an operation. Then you're adding on another operation. That then do this is adding something that you need to do. So when you're doing something like going east 3 miles and north 5 miles, does it matter which you do first? No, I'm probably going to end up the same place if I go east 3 miles and then north 5 miles, or if I go north 5 miles and then east 3 miles. Those are going to put me in the exact same location. That's how maps work. And it turns out that we can actually show that graphically here on this page. If I was to take a vector A and add a vector B to get some resultant C, that's the same thing as taking that same vector A, the same vector B, but doing B first and then A afterwards. This blue vector here, this blue vector here, those are the same thing. So that is what it means to add. And so we could add 3 vectors. We could add 4 vectors. We could go on and on and on. And it doesn't really matter which one we do first or which one we do last. It's just a matter of us doing all of them. Okay. So that's what it means to add. And sometimes we add 2 vectors that are in the same direction. Maybe we're adding 2 vectors that are in opposite direction. That's totally fine. In fact, if what we're doing is going in the opposite direction, we're going in the negative direction of the other. So moving in the positive x direction is moving to the right. Moving in the negative x direction is going to the left. But both of those are x's. It's just the sign that tells us which way we're going. Interesting, interesting. And actually, subtraction is very similar. What we're actually doing with subtraction is adding a negative. Adding a negative, what do you mean? Well, the negative of a vector is a vector with the same magnitude pointing in the opposite direction. So if I'm subtracting one vector from another, what I'm adding is the negative of a vector to another vector. And on this page, maybe this is fine, but it's a little bit more understandable by playing with it in real time inside Mathematica. So let's look at subtraction a little bit here. If you're curious, all of these vectors are the same. All of these vectors are the same. Same magnitude, same direction, different location, and that's totally fine. I have a little Mathematica simulation here where we can talk about addition. Not a big deal. But I wanted to talk here about subtraction. And here what I have is 2 vectors. And I've got a vector A, I got a vector B. A is the red, B is the green. And what I've put together here is some combination where I can move them together and add them. So if I wanted to have A, which is red, and I wanted to add B to it, I'm doing something like this. And I would get some resultant C, whatever you happen to want. And I could change, I'll worry about what that is later. But let's say we wanted to change orientations. We want to change orientations. Let's do B is here. Maybe it points like this. Something along those lines. Okay. So now we've got these 2 vectors. If we add them together, we would get something like so. But I would like to subtract. And what I'm saying I'm doing when I subtract is I'm adding something to the negative of the other. So let's say I wanted A minus B. That would be adding A to negative B. And if I was to add A to negative B, what I should get is a vector that points from the tail of red to the head of green here. A minus B is doing exactly that. Interesting. What is another way to talk about A minus B? So we have A and B. I'm going to put both of them at the origin like so. You'll notice that this blue vector also points from the head of one vector to the head of the other vector. This is A minus B, right? So if I was to subtract B and add A, yeah, I'm going from the head of one vector minus B plus A to the head of another vector. A minus B goes from the head of B to the head of A. Okay. Well, what if we wanted to do B minus A instead? So here's B and here's minus A. what if I add those two together? B minus A. That should be a vector that points down and to the left. B minus A. Down and to the left, just like it's supposed to. And similarly, if we were to have A and B positive, both of them sitting at the origin, this blue vector points B minus A. So we go minus A, then we do B. That's what this is doing. It's pointing from the head of one to the head of the other. And it's different than what it was before. A minus B and B minus A, have the same magnitude, opposite direction. Same magnitude, opposite direction. That's how that works. Okay, so as we're doing addition, as we're doing subtraction, that's really what's going on. Now, there's a lot that we're doing with addition and subtraction. Addition and subtraction, particularly with vectors, is not easy. But what are some other things that we would like to do? Let's go here. Go back to OneNote. Maybe we want to do addition with components, or subtraction with components, which is really exactly the same thing. So here is where we're taking some vectors. We have a way to use trigonometry and break off the x part, the y part, how they go in different directions. If I'm adding two vectors together with components, I would just add the x components together to get a total x. I would add y components together to get a total y. Sometimes this is easier to do than just working with vectors by themselves. This is why we do it. And graphically we can see that's totally fine. This blue vector right here is the sum of A and B, as you can see graphically. But if I was to do the x component of A and the x component of B, this is the x component of that blue vector. If I was to look at the y component of A, the y component of B, and add those together, that is the y component of that blue vector. So we can see graphically that adding A and B to get a resultant is the same thing as adding AX and BX in the x direction, adding AY and BY in the y direction. This is a total x, total y. And while this picture doesn't show it, components can be negative and it works the same way. Maybe we have one vector that's going to the right, another vector that's going to the left. If we add them together, we're really looking at the difference between those because we went to the right and then we went back to the left. So it is minimizing that distance again. So when we're working with components, sometimes it's easier to use the components and sometimes it's easier to use the vectors themselves. That's what we have to determine as we're doing different problems. Now, there are actually a couple of ways to do multiplication of vectors. The first one is just boring, taking a vector and multiplying by a number. And that number could be some integer, but it could be a real number too. Multiply by pi, multiply by the natural base e, whatever you want. 1.7, I don't know, whatever you want. But all that does is change the length. You can't really change the size of the unit because the unit is what it is. But what you are algebraically doing is changing the number that was in front of that unit before. So say you had a vector A. It was a certain size. It pointed in a particular direction, right? If I was to double that vector, it's still going to point in the same direction. It's just going to be twice as big. That's kind of how numbers work. So similarly, maybe we can even multiply by negative numbers. That's totally fine. It just means that now we've got a vector that's also pointing in the opposite direction. And that's totally, totally fine. But more interesting ways to do multiplication are things called the dot product and the scalar product. The dot product, what we're doing is taking two vectors, we're multiplying these two vectors together, but once we've done that multiplication, the thing that we have left over doesn't have any direction. And this actually really comes up in physics courses. We multiply two vectors together and we get something that doesn't have any direction. This is something that we're going to get when we talk about energy in a couple of weeks. Energy is a scalar that comes about because of multiplying two vectors together. This particular operation is called the scalar product or the dot product. And what we're doing is taking two vectors and putting them in. One vector is coming out. And it's written, and it's called the dot product because the operation is written with this dot. Now graphically, the way you calculate the dot product is you look at the component of some vector in the direction of the other vector. And then you multiply, so here the component of B in the direction of A times the magnitude of A. So A has a magnitude. There is a component of B in the direction of A. That's some magnitude. You multiply those two things together. Now what if we had B that was perpendicular to A? Well, then there is no component of B in the direction of A, and so that would be 0. That's something that has a dot product of 0. The two vectors aren't 0, but I multiply the two vectors together, and the result is 0. Similarly, if B and A were in the same direction, the component of B in the direction of A is B. B times A. And so if the angle between those things is 0, then I'm just multiplying two numbers together. And that's totally fine. Those numbers happen to be vector numbers, we find out later. But the result is a scalar, and it works very much the way that you might think. Now graphically, the way we can figure out the component of B in the direction of A is to look here through trigonometry. The component of B in the direction of A is this thing notified here as B cosine theta. This is the component of B in the direction of A. So B cosine theta times the magnitude of that vector A is AB cosine theta. And so if I can measure that angle between B and A, I can find the dot product of A and B by knowing the magnitude of A and the magnitude of B. But it turns out that if we write both A and B in terms of their components, this can be convenient as well. So maybe I want to write A as AX in the X direction, AY in the Y direction, AZ in the Z direction. I want to write B as BX in the X direction, BY in the Y direction, BZ in the Z direction. These are the components in these directions. If I was to take a component of A in the direction of B times that magnitude of B, I can work with it purely in the X direction. I can work purely in the Y. I can work purely in the Z. And sometimes these things could be 0. One of these or multiple, it could be 0 here in A's or here in B's, whatever. But essentially what we're told is that this is going to be AX BX plus AY BY plus AZ BZ. This component form of the dot product, this magnitude and direction form of the dot product are the same thing. They are the same number. And so we can use those two definitions to do all kinds of things. We can measure the angle between two vectors. We can make sure and confirm that two angles are perpendicular or not perpendicular. And here I've actually shown that with, hey, we got these two vectors, A and B, written in different ways. So there's 90 degrees between them. They point in weird directions, sure. But I can find all those various components, and lo and behold, A dot B is 0, even though A is not in the X direction and B is not in the Y direction. They only need to be perpendicular, and it's still going to be true. We can use the dot product to find the length of a vector, because if we were to take a vector length dotted with a vector length, we get a length squared, but no direction. So I take the square root of that thing, and lo and behold, I've got the length of a vector by taking the dot product of a vector with itself and taking the square root. And that's where the Pythagorean theorem came into play for something like that. So this is a dot product and how we would find the dot product of two vectors in general. But sometimes what we want to do is have two vectors, multiply two vectors together to get another vector that is something that still has direction. So the dot product, I took two vectors, multiplied them together, and got a scalar. With this, the cross product, called the cross product because there is this x in there, the way we signify this type of multiplication, is taking two vectors, multiplying them together to get a vector that comes out. Is that, yeah, so this is what I want. So, the way we find vector product is we are basically taking a vector cross another vector, but what it is doing is keeping track of how these vectors are perpendicular to each other. I feel like I'm missing a page here. Dot product properties, no. Cross product, this is what I want. Yeah, so that's it. So when we're dealing with the dot product, we have this angular approach, component approach. With this vector product, this cross product, what we're doing is actually finding a component of a vector perpendicular to another vector times the magnitude of that other vector. And then the direction is determined by something called the right-hand rule. And graphically, we would be doing something like this. So let's go back to this picture. With the cross product, we're finding the component of B perpendicular to A. In this picture, that would be B sine theta times the magnitude of A, which is A. And so the perpendicular component of B times the magnitude of the vector is AB sine theta. But it turns out that the result has to be perpendicular to both of these vectors. And the way we determine which direction to point is used by something called the right-hand rule. Crossing a vector A into a vector B says first place A and B tail to tail, point your fingers of your right hand in the direction of A, close your hand in the direction of B, your thumb points in the direction of the result. This is called the right-hand rule. Does it discriminate against left-handed people? Actually, quite the opposite. If you are right-handed, that means you are writing with your right hand. And so on an exam, when you are doing right-hand rule, you need to put your pencil down so that you can use your right hand. Left-handed people, they can write with their left hand, do cross products with their right hand, and everything is fine. So if anything, the right-hand rule discriminates against right-handed people on an exam or when doing homework. But this is a type of result that's taking a perpendicular component times a vector. The direction of the resultant is perpendicular to both of the input vectors. Now the magnitude of this doesn't change if you were to swap A and B, but the direction does change if you were to swap A and B. So here A cross B is pointing in the C direction, B cross A points in the D direction. D and C have the same length, but D and C do not have the same direction. And so there's a little bit of math here that shows why which way is one versus the other. And we have cross product properties and everything else. Now I do have some Mathematica that talks about the dot product and the cross product, and that's totally fine. But let's say we wanted to look at one particular application and see if we could figure out something about it. I want to look at this problem. And this is actually a problem that I have looking at vectors A and B in the demo videos, the example videos that I already have on Canvas. I'm going to instead, for this problem, look at vectors B and D. And so we've got a coordinate system. This is the x direction. This is the y direction. In the book, he uses IJK coordinates. I think IJK coordinates suck because how do I know what the I or J or K coordinate direction is? Why not just call it the x direction? Call it the y direction, call it the z direction. Why not make this easy? So I am going to use x, y, and z hats and not I, J, and K hats. And so that's just something that I guess you have to prepare for. Now in this problem, we have B that's pointing in this direction. And what we're told for a vector direction is that we got some angular measure measured with respect to the y-axis. Now we happen to know these numbers. B has a length of 15, theta has a magnitude of 30 degrees, but I don't want to worry about that yet. The way we work with these vectors is no different if B had been 12 and theta had been 20 degrees. All of the trigonometry should work the same. The way we add things together should work the same. Nothing should be different. So let's not make anything harder than it needs to be. We also have a vector D that has an angular measure with respect to the y-axis shown here as a vector phi. Now phi happens to be 53 degrees here, fine. D happens to have a length of 10 meters, fine. But from this, just using trigonometry, we can find out a lot about these vectors. So for example, from trigonometry, if we wanted to find out what the components of B are, we see that B is to the right, we see that B is up. So how do we find out the components? Well, the x component of B is associated with this right triangle here. This is the opposite side, so B sine theta in the x direction. The adjacent side is B cosine theta. This is how we can express B in terms of coordinates. If we wanted to look at D, we can do the same kind of thing. D is to the left and D is up. So how do we find out how far to the left? We have to look at this right triangle. This to the left is the opposite side of the angle. This is minus D sine of phi in the x. It is plus D cosine of phi in the y. So even though in the problem we're told magnitude and direction for each of these vectors, we can write the components of these vectors if we wish. Now how big are these different numbers? So we can point these things out. Let's pull up a calculator here quick. So we've got sine of theta, which is 30 times sine times 15. So this is 7.5 meters. Now we've also got a B cosine theta. So theta is 30 degrees. Cosine is this times 15. 12.99, so 13.0 meters. So it's going more up than it is going right. And that's what it looks like from the picture. Okay. Now let's say we're looking at phi instead. So phi is 53 degrees according to our picture, so sine of 53 times d, which is 10, times negative 1, minus 7.99 meters in the x, and 53 cosine times 10 is 6.02 meters. So sure, it is going a little bit more left than it is going up, but that's also what it looks like from the picture. Now given this, there's a couple of other things that we might want to do. What if we wanted to find B plus D? The way we find B plus D is, graphically we could have put things together, but I know these components. B plus D is B sine of theta minus d sine of phi in the x. I'm taking this, I'm adding this for the y direction. B cosine of theta plus d cosine of phi in the y. I'm taking this, I'm adding this. Now these things carry sign, and that's totally fine. But if I wanted to, I could actually figure out what this number is going to be. So what is this number? We pull up our calculator. So theta is 30 sine times 15 is equal to this minus 53 sine times 10 minus 0.486 meters in the x, and for y we've got 30 cosine times 15 plus 53 cosine times 10, which is 19. So as we look at this, we see that b plus d, we went right, we went left. I went right 7.5, I went left 8. And so when I do the resultant in the x, it's minus a half, as we might expect just from numbers. I went up 13 and then I went up 6. That's the same thing as going up 19. Okay, so numerically, that works. What if I wanted to look at b minus d? Now again, this is going opposite d plus b. That is the same thing as starting at the tail of d, subtracting d, adding b. I should get a vector that looks like this. This is b minus d. So it should be to the right, it should be up. How would I write this? B x is b sine theta minus d is plus d sine of phi. That's what's going on in the x. These really carry signs. Plus b cosine theta minus d cosine phi. This is what's going on in the y. So what's this magnitude? What's this magnitude? Let's clear everything and take a look. So theta is 30. So 30 sine times 15 is equal to this, plus 53 sine times 10 is 15.5 meters. Over here on the right, we have b cosine of theta, so 30 cosine times 15 minus 53 cosine is 10, 6.97 So as you might expect, I'm moving 15.5 to the right, 7.5 plus 8. Okay. So this is 7 up. Well, B was 13. D sub y was 6. The difference between that is 7. 7. So yeah, I went right 15.5, up 7. That's what that vector is doing. So B minus D really does look like this. What if we wanted to do B dot D? Well, the way this works is we take the x components of B and D, multiplying them together. Those are the x components of B and D. The y components of B and D. Look like so. And we can actually simplify this further. Each of these is going to have a B and a D. But now what we have left over is a cosine theta, cosine phi, minus sine theta, sine phi. Now you guys might not remember the trigonometric yell, but the trigonometric yell being sine, cosine, cosine, sine, cosine, cosine, sine, 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 is how we know how to work with this. Cosine, cosine, sine, sine, sine. This is the cosine of theta plus phi. That's what this is. What is the angle between B and D? Theta plus phi. B, D, cosine of the angle between. We see it through components. We see it graphically. They are the same thing. What is this number? Let's pull out our calculator. So theta plus phi is 30 plus 53. Almost 90 degrees, but not quite. Cosine of that angle is something very small, times 15 times 10, 18.3. And this is meters squared, and there is no direction. This is a dot product. Okay. Well, what if we wanted to do B cross D? Maybe you're not familiar with finding determinants of matrices. That's fine, but this is a technique we have in the book. We're going to talk more about cross products as the term goes along. But we have B in the x direction, so the x component, B sine theta. The y component, B cosine theta. We have no z component. Now we look at vector D. Its x component is minus D sine phi. Y component is D cosine of phi, but it also doesn't have a z component. When I find the determinant of this matrix, this times 0 is 0. 0 times this is 0. For the y, 0 times this is 0. This times 0 is 0. But for z, I've got a BD sine theta cosine phi, and these two things multiplied together with a minus sign turns into plus BD cosine of theta sine of phi. So putting this together, this is BD sine theta cosine phi plus cosine theta sine phi. If we remember the trigonometric Yale, sine, theta, sine, cosine, cosine, sine, cosine, cosine, sine, 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 this is sine of theta plus phi. Now we've got a direction here. This is all in the z direction. So we've got B, D, sine of the angle between theta plus phi in the z. And numerically, we can find this as well. We've got 30 plus 53. Sine of this angle is going to be close to 1, but not exactly, times 15 times 10. This is 149 meters squared in the z direction. Now note here, B cross D, for the right-hand rule, you see my right hand here, B cross D comes out of the page in the z direction. So putting all this together, this is a perfectly valid way to talk about directions and magnitudes and how things are going to work. I'm going to show in just a little bit that maybe we could look at this problem in a slightly different way and get different results. What if we have the same coordinate system we have the same vectors, let's do this, only I'm going to measure both of these vectors not as pictured. I'm going to call this vector theta, or vector alpha, and this vector beta. Now, this beta is really just 90 degrees plus what we called phi before. So this is 143 degrees. 143 degrees. But this alpha, this is just 90 minus what we had as theta before. Which is 60 degrees. Now the difference is both of these angles are measured with respect to the positive x-axis. So if I wanted to look at what is B, B is the magnitude of B, cosine of alpha in the x, plus magnitude of B, sine of alpha in the y. What is D? It is D cosine of beta in the x, D, sine of beta in the y. I don't have to think about sines. I don't have to carry around sines. Those sines will work the way that they're supposed to, as long as I'm always measuring these things with respect to the x-axis going around counterclockwise. Okay? So let's pull up our calculator again. How do these numbers compare to what we saw before? Well, now alpha is 60. 60 cosine times B, 7.5 meters. Sorry. 60 sine times 15, 12.9, 13.0 meters. What if we're looking at D and the components of D? Now beta is 143, 143 cosine times D, which is 10, minus 7.99, meters. And 143, the sine of that, times 10, 6.02. meters. How do those numbers compare with what we saw before? 7.5, 7.5, 13, 13, minus 8, minus 8, 6.02, 6.02. They work exactly the same, only this way didn't require any thought. I didn't have to code in any signs. The signs came out for free. That's very nice. Well, what are some other things we might concern ourselves with? We could concern ourselves with b plus d, and that will be b cosine of alpha plus d cosine of beta. And the x, b sine of alpha plus d sine of beta in the y. Okay. Well, what about b minus d? The same kind of thing that we did before. But now this will be b cosine alpha minus d cosine beta. B sine of alpha minus d sine of beta. And the thing is, casually, we throw in some numbers, you're going to find out that this number and this number are the same as they were with the other technique. This number, the same as they were with the other technique. The only difference is if I measure with respect to a common axis, I don't have to think about the signs. So this cosine of alpha, in this case cosine of beta, is going to be negative. This is going to be something that's added on, as we expected. Sine of beta, well, that's going to be positive. That's totally fine. It's going to work exactly the same as it did before. In fact, the two interesting ones, b dot d, is now going to be b d, and we're going to have a cosine of alpha, cosine of beta, plus sine of alpha, sine of beta, from the trigonometric yell, cosine, cosine, sine, sine, sine. This is cosine of alpha minus beta, which is the same thing as the cosine of beta minus alpha. Cosine of 10 is the same thing as cosine of minus 10. Cosine of 90 is the same thing as cosine of minus 90. So putting a minus sign through that is not a problem. This is the angle between these two things. Beta minus alpha, beta minus alpha. It's the angle between. Cosine of the angle between, just like it was before. This has to be the same number. It has to be the same number as we had before. If we were looking at cross products, the x component of b cosine of alpha, b sine of alpha here. For d, we've got d cosine beta, d sine beta. Putting it all together, this is b d, and we will have cosine of alpha sine of beta minus sine of alpha cosine of beta. moving up just a little bit, moving a minus sign, minus BD, sine of alpha, cosine of beta minus cosine of alpha, sine of beta. This is the sine of alpha minus beta. And with that minus sign, Z, Z, Z. Beta minus alpha, the angle between the two vectors. The angle between the two vectors, just like it was before. Sine of the angle between those two vectors, B and D. They're the same length as they were before. It's still pointing in the Z direction. This is exactly the same thing. And the only reason why I'm doing this comparison is because I didn't have to code any negative signs into this. I just had to say x component is the cosines, y components is the sines. They're all going to be positive, and if a negative pops out, it's because the cosine is negative or the sine is negative. That's why it pops out that particular way. So through this process, we've seen a couple of different ways to talk about addition, subtraction, multiplication as dot products, cross products. And we've talked a couple of different ways to use the trigonometry, sometimes using vectors that are expressed with respect to an arbitrary coordinate system, sometimes not, with respect to a universal coordinate system, like I've done here on this page. So while this is perhaps a little bit longer than I anticipated, I hope that this was a helpful look at looking at vectors.